And our next speaker is Dieter Lüst from Humboldt University, who will speak about intersecting brane worlds on Calabi Yau orientifolds.
So first of all, I'd like to thank the organizers for the invitation to this very nice conference. The work I'm going to report on was done in collaboration with Ralf Blumenhagen, Volker Braun, and Boris Körst, and appeared in this preprint here. So I think we all agree that one of the main goals in string theory is still to find a realization of the standard model. And just to remind you, the key properties of the standard model are that you have to have a non-abelian product gauge group with 3 generations of chiral matter. As we will discuss, and probably as Louis Iban has already convinced you, intersecting brane worlds provide a promising avenue of approach to this goal. On Monday, I think it was, Stephen Giddings gave a very nice talk on warp compactifications. But he also remarked at his end that he needs a little module to plug into his construction. Then the module is the standard model. So we are aiming to construct this module. Of course, we have to see at the end whether everything is compatible or the whole system breaks down. Let me just recall very briefly the origin of chirality and non-abelian gauge groups in string theory. Namely, we have historically 3 kinds of constructions: the heterotic string, the type 2 superstring, and also M theory. So in the heterotic string, charges of non-abelian gauge groups in chiral fields simply, or not simply, it's quite subtle, arise because of the different treatment of left and right moving string modes. In the type 2 superstring, D-branes and orientifolds provide a very nice tool to get chiral spectrum and charged fields. So here they arise in the open string sector on the D-brane. Finally, in M theory, the situation is perhaps even more subtle. Namely, you have to put M theory on a singular space, for example, on an interval, in order to get charged chiral spectrum on these singularities, so on the end of the world branes. Of course, we like to preserve the chirality also upon compactification. So in the heterotic string, chirality requires some non-trivial topology of your 6-dimensional compactification manifold, which has to be equipped with an additional structure with some vector bundles. So the chiral index there in general is given by the third Chern class of the vector bundle, or in simple cases where you identify the vector bundle with a tangent bundle, it is given by or determined by the Euler number of the internal space. In the brane construction, we are going to tell about, or we're going to discuss, chirality is preserved or transported to 4 dimensions if your internal space allows for non-trivial intersection numbers. So the chiral index is given by intersection number. It's the intersection numbers of certain homology cycles on the internal space. And this will be the main issue of the talk. Finally, in M theory, chirality requires that the internal space exhibits certain singularities. For example, if your 7-dimensional space possesses point-like singularities, so it's a kind of a cone with an apex, then the chiral structure is determined by the base of this cone. In simplest cases, again, you get the Euler number of this 6-dimensional base. Of course, in any string theory, you have to obey microscopic string consistency conditions. In the heterotic string, they come from the worldsheet modular invariance, and you can show that this is intimately linked to the issue of target space anomaly freedom, of target space anomaly cancellation. In the type 2 brane constructions, the open string provides microscopic string consistency requirements, namely the so-called cancellation of Ramond tadpole charges, And again, this will ensure anomaly freedom in target space. Finally, in M-theory, there are no really obvious microscopic consistency checks, but there's a very nice procedure of so-called local anomaly cancellation by inflow mechanism on the singularities. And this gives you also a very nice tool to handle the spectrum on these M-theory compactifications. So the further plan of my talk is that I will first discuss in some detail intersecting brane worlds on Calabi Yau spaces, and then, at least for those which preserve n=1 supersymmetry in 4 dimensions, I will also make some remark on the lift to M-theory via G2 manifolds. So an intersecting brane world is constructed essentially in 3 steps. First, you pick some certain closed string background. So say our 10-dimensional space-time is given by the product of 10 minus 2D dimensional Minkowski space times some 2D dimensional internal manifold. In the next step, we apply the orientifold procedure, which means that we get an orientifold 9 minus D plane. And this, to remind you, is just essentially an orbifold construction where we divide the target space by omega times sigma bar, where omega is worldsheet parity and sigma bar is some anti-holomorphic involution which acts on D coordinates of the internal space. And then this fixed point locus of sigma bar defines some certain D cycle in the internal space, which is called orientifold plane. Then we add, of course, D branes, D9 minus D branes, which are space-time filling, so the world volume entirely fills Minkowski space-time, and in addition is wrapped on some homology D cycles in the internal space, which we call PA. Then the massless spectrum first is given by supergravity in the 10-dimensional bulk, and since we have this orientifold, the number of supersymmetries is reduced by half, so we are dealing with cases of n=4, n=2, or n=1 supergravity in the bulk. Then, secondly, we have gauge fields which are localized on the 10 minus D dimensional world volume of the D branes. Again, due to the BPS nature, essentially, of the D brane supersymmetry is preserved to a certain amount. And finally, there's chiral matter localized on the 10 minus 2D dimensional intersection points of 2D branes. And here, supersymmetry can be either preserved or it can be even completely broken, which depends on essentially on the location, on the angles of the branes. And the important point is now that the number of chiral fermions is given by the topological intersection numbers between 2D branes, or also between a D brane in an orientifold plane. Let me quickly first give an overview. Excuse me. Yeah, let me first quickly give an overview over the models studied so far. As Luis Ibanez already reported, mainly the construction was limited so far on toroidal models. Here, indeed, one can construct, I think, quite attractive intersecting brane world models with the standard model gauge group and 3 generations of quark and leptons. The discussion started following the nice paper of Kostas Bachas in 1904 in this work where we showed how the consistency requirements of intersecting brane world models can be met, and then also to a large extent by the group in Madrid by Ibanez, Rabadan, Uranga, and others, and also several other people contributed. This field was developed further. Then, if you want to have supersymmetric brane world models, you have to have necessarily some orbifold construction. So, for example, Svetic, Shiu, and Uranga constructed a T6 or over C2 times C2 overfold, which is supersymmetric. One can also derive various gut models by orbifolds. And it's also, I think, quite interesting to study the potential. I will remark on those potentials a little bit later. Namely, they give a rather economic way to realize inflation in this kind of brane models, which was discussed by Burgess, Majumdar, Nolte, Quevedo, Rajesh, Sang, also others. And we also showed how these hybrid inflation models, taking account certain restrictions, can be built in intersecting brane world models. So now let us discuss how these constructions are generalized not only to flat backgrounds, but say to K3 manifolds, or in particular to Calabi Yau spaces. And the point I like really to emphasize is that the spectrum can be, the open string spectrum can be still derived, nevertheless, that the metric of these spaces is not known. Namely, the whole information on the spectrum we need to derive the four-dimensional effective action is essentially decoded in the topological quantities of your embedding space. So first, as I have said already, we choose an orientifold 9 minus D plane. And this is usually done in local coordinates that the orientifold or the sigma bar action acts on the imaginary part of the complex coordinates in this way. And then you can show by the action on the holomorphic 3 form and also on the Kähler form that the orientifold plane, which is the fixed locus of this symmetry operation, is indeed a supersymmetric special Lagrangian cycle, a D cycle, which implies that the pullback of the Kähler form and the pullback of the imaginary part of the holomorphic 3 form is 0, and that the pullback of the real part of omega D is given by the volume. Next, we introduce NAD 9 minus D branes, which are also wrapped on supersymmetric cycles. But for those D branes, we only require that they are calibrated not with respect to the same, say, phase as the orientifold plane, but we allow that there's an arbitrary phase here in the calibration of the D branes, which means that there's a kind of weak individual supersymmetry conservation on each of the branes, but mutually these branes may break supersymmetry and also say with respect to the orientifold plane. So to get the restrictions on the spectrum, we have to study the effective U-engaged theory on the D branes. This effective action is first given by the bulk part, by the gravity part, where G, B2, G is symmetric, B2, the antisymmetric tensor, and then we have moduli and several form fields. The more important part for us is the brane effective action, which splits into a tension part into another part which describes or which encodes the charges of the brane, which is given in terms of a Chern-Simons action on the world volume of the brane. So let us first analyze quickly the requirement of Ramond charge cancellation. The world volume P, to remind you of the D branes, is 9 minus D. So this action is given in terms of a tension, in terms of the so-called Chern character of the gauge fields of the gauge bundle which lives on the brane. And then we have also the ratio of two Dirac genera, namely of the pullback of the curvature transversal and also normal to the brane. But in our situation, where the gauge fields are essentially flat and where the brane supersymmetric is calibrated, this expression just reduces to the rank of the gauge group times the highest form which appears in this expansion. And if you then look at the equation of motions of the gauge form Cp plus 1, you get a topological restriction on the number, on the allowed number of D branes, and also on the allowed homologies of cycles where you can wrap your d-branes around, namely this condition has this form. It is an equation, as I said, in homology, so it comprises in general several equations. Here we have the contribution of the d-branes. PA denotes the homology cycle of the d-branes. PA prime denotes the homology cycle of the mirror brane due to the orientifold reflection. And the negative contribution obviously is a part from the orientifold plane. Then if we look at the other part of the effective action, namely essentially the volume of the branes, this gives you, or the tension of the branes, this is a Dirac-Born-Infeld action, and this piece of the action gives you an effective d-term potential in, say, 4 or in lower dimensions. And this effective scalar potential is essentially given by the volumes of the various branes minus the volume of the orientifold plane. This potential in general does not vanish, so it means that some of the moduli are generically are moving and are possibly unstable. However, it is easy to show in the case of n-equivalent supersymmetry, where all branes are calibrated with respect to the same d-form as the orientifold plane, the scalar potential vanishes identically. So it is also very clear that to build supersymmetric models, the orientifold planes are necessarily needed in order to cancel the charge and the tension of the d-branes. So now let's be a little more specific. Let's go to, let's consider a 6-dimensional Calabi Yau space. So the picture is as follows. We have wrapped the 6 branes. The gauge fields live on the 7-dimensional world volume of the 6 branes, which are wrapped around slack 3 cycles, so there are codimension 3 in the Calabi Yau space. And the chiral fermions then live at the intersection of the 6 branes, which are codimension 6 in the Calabi Yau space. So you have this little picture. The intersection is the 4-dimensional Minkowski space, and here in this direction we have 3 possible 3 cycles inside the Calabi Yau. As I told you, we can now compute the fermionic spectrum in terms of the intersection numbers, and depending whether you have an intersection of, say, a d-brane with another d-brane, or a d-brane with a mirror brane, or a d-brane with an orientifold brane, you get these various possibilities of intersection numbers, which correspond to certain representations of your effective gauge theory. So you get antisymmetric representations of UN, symmetric representations, and most important for us, as Louis Iban has already discussed, 2 kinds of bifundamental representations, which are just given by the intersection numbers of a brane wrapped around a cycle A and another brane wrapped around a cycle B, and here we intersect a brane with a different mirror brane. Note also that this intersection matrix is anti-symmetric, so there are no safe interactions, which means that there are no adjoint matter fields on Calabi Yau spaces. So let me quickly give an example, and I think the simplest example of a smooth Calabi Yau is Fermat quintic. Maybe I should say before, you can of course test these formulas also in various orbifold constructions, and then you get, of course, what you can directly calculate from studying string partition functions. This is in particular need to say how this works out for K3 compactifications, where you can obtain by relatively simple means previous constructions like the Gimon-Polchinski orbifold, where some effort had to be spent to compute the corresponding open string partition functions. Okay, now let us look quickly to the Calabi Yau, to the quintic Calabi Yau. The orientifold 6 plane is just defined by putting the imaginary parts in this equation to 0. So this defines a particular three-dimensional supersymmetric cycle in this way while they're embedding in RP4. And now in order to construct the other cycles around which the D6 branes erupt, one can apply the underlying Z5 to the 4 symmetry. This gives you in total 625 supersymmetric cycles which are calibrated with respect to some phase. And moreover, you can show that 125 of these supersymmetric cycles are calibrated with respect to the same phase as the orientifold 6 planes, which means if you wrap D-branes around those, you get NQ1 supersymmetric models. The intersection numbers follow from a nice paper by Brunner, Douglas, Lawrence, and Römelsberger. I don't want to go into this discussion, but you can show that if you restrict the D-branes only to be wrapped around the 125 supersymmetric cycles, that those have unfortunately 0 intersection number. So from the quintic, we do not get any non-trivial supersymmetric model. Of course, you can try also to wrap D-branes around the other cycles, which means that you are constructing a non-supersymmetric model. And here, indeed, we found a non-supersymmetric realization of the standard model from the quintic, namely, very briefly, you introduce, like Louis was already discussing, some lengths, 4 stacks of the 6 branes. 1 stack corresponds to the color branes, the second stack is the SU2 brane, and then we have 2 further U1 branes. You choose the following wrapping numbers. In fact, it's convenient to set up a little computer program, and then you see that in fact you get 3 generations of quark and leptons. Okay, so now finally in the last 5 minutes or so I want to discuss how you lift up these models to M-theory in case they are supersymmetric. Very briefly, the following singularity play an important role in M-theory compactifications. First, you can imagine that you have codimension 1 singularities. So in the simplest case, you deal with M-theory on an interval times a 10-dimensional space. This is known as heterotic M-theory, and these 2 codimension 1 singularities in particular support E8 gauge fields or a subgroup of E8. You can also generalize this for more elaborate orbifolds to get models in 6 and 4 dimensions. Then, and this is the issue which is interesting for us in the context of brane constructions, you can have codimension 4 singularities, in particular, say, AN singularities of this form. And indeed, as it is known for some time, this is the M-theory lift of n plus 1 D6 branes, since in M-theory, the whole D6 brane geometry, including the Ramond gauge field, is completely described by metric degrees of freedom. And finally, you can have codimension 7 singularities, and these singularities will turn out to be the lift of the intersection points of the D6 branes which support chiral fermions. So to get a concrete realization of it, one has to study, as we know, G2 M-theory on G2 manifolds. The type 2A is reobtained by dimensional reduction, namely one assumes that the 7-dimensional space has a abelian S1 isometry, which means that one deals with a circle fibration of this form. So you have a 6-dimensional base, which is, say, the background geometry of the type 2A string in this case. This 6-dimensional base is in general non-Ricci flat, and due to the dimensional reduction, you also reobtain the dilaton field and also the Ramond-Ramond one-form potential. So the singularity structure, which was in particular discussed by Atiyah and Witten, and also by Acharya and Witten, and also by many others now, is that if the S1 action has fixed points in codimension 4, these fixed points correspond to the 6 branes which are wrapped on the 3-dimensional fixed point set L, call it inside X7. And furthermore, if there are isolated conical singularities of codimension 4, which means that somehow two codimension 4 singularities collide into a point-like singularity, this should then describe the intersection point or the intersection locus of the D6 branes. So in this case, the 7-dimensional metric has the form of a cone over some 6-dimensional base space Y6. And again, this 6-dimensional base space in general is non-Ricci flat. It has to have weak SU3 holonomy, which means that the imaginary part of the holomorphic 3 form is not anymore closed, but it's given in terms of the wedge product of a certain 2 form omega with itself. So now let's try to see whether one can get metrics which correspond to intersecting the 6 branes. And in fact, as you know, for the compact case, it is so far not known how to construct G2 manifolds explicitly. So we have to restrict ourselves to non-compact metrics, which means that we are essentially zooming, if you wish, at the locus, at the point where the D6 branes are, or even more at the points where the D6 branes intersect. So you get a local picture of, in general, a more global construction. So a nice class of these G2 manifolds can be constructed as an R3 bundle. It's a certain twisted R3 bundle over a 4-dimensional quaternionic space Q. The 7-dimensional metric is given then by this equation where ds4 is the metric of the 4-dimensional quaternionic space, and the 3 UIs are the coordinates of R3. In fact, there are several known examples of so-called cohomogeneity 1 metrics, namely in the first case, the quaternionic space is the 4th sphere, the 6-dimensional base of the cone is CP3, and this corresponds to 2 intersecting the 6 branes, as was discussed in particular by Attia and Witten, and also later by Berglund and Brandhuber. There's a second nice example where the quaternionic space is CP2, and this in fact corresponds to 3 intersecting the 6 branes. So let me very quickly, in the last perhaps 2 minutes, if the chairman is patient, discuss a generalization of these spaces, which we considered recently together with Klaus Berndt, Gianguido Dall'Algata, and Swapna Mahapatra. Namely, the idea is simply to consider more general quaternionic 4-dimensional spaces with only 2 U1 isometries. In the previous cases, as you saw, these were homogeneous spaces which had more symmetry. So we want to use essentially more general spaces which allow for 2 U1 isometries. These spaces are known, or a class of those spaces is known in the literature. They were considered in the context of rotating black holes by Plebanski and Demyansky. The metric of the quaternionic space has this form, determined by 2 polynomials of 4th degree in the coordinates P and Q. And now you have to turn on the machinery. You have to perform the dimensional reduction of the space over a U1 isometry. So you have to pick a certain killing vector, and you have to determine the fixed point set. And to show you very quickly how this goes, for example, for this type of killing vector, which is determined by the parameters R1, R2, R3, R4 of the metric, you get certain fixed points which are codimension 4 essentially in the quaternionic space. So they are indeed also codimension 4 in the total G2 manifold. And okay, maybe time is a little too short now to enter a more detailed discussion. You can show that indeed those fixed points of those metrics lead to 2 D6 brane loci which are positioned, the coordinates are given are positioned at those values. And following the arguments by Acharya and Witten, these indeed should correspond to 3 stacks of the 6 brane gauge group SUN times SUN times SUM. So indeed we believe that this might correspond really to the G2 metric of the case where, or which is related to the weighted projective space WCP2 with parameters N, N, and M. Okay, I think I summarized my talk. I hope you are a little bit attracted by this construction of intersecting the 6 branes on Calabi Yau spaces, namely they, in my mind, provide an interesting framework in order to construct models which have very attractive phenomenological problems. The main point is that the Kyle spectrum is determined by topological quantities, in particular topological intersection numbers. Of course, you can also discuss issues now of stability, of constructing superpotentials. This would connect nicely to the talk of Wafa. And finally, they, in a way, if they are supersymmetric, provide an existence proof of G2 manifold, but it is very hard to construct, I think, explicit models with compact G2 spaces. Thank you.
Okay, thank you. Are there questions? Any questions? Am I missing someone? If not, we'll come back. If not, we'll come back in 25 minutes. Okay, and we'll start then at 4:52 or something sharp. Anyway, let's thank the speaker again.